Hello everyone, this is Team 34. We are going to present analysis and redesign of a belt and disc sander. As the background of the product, sanders are used to smooth wood or metal surfaces. A motor is used to turn two shafts that spin each sanding phase at high speeds. The vertical belt offers more flexibility, while the disc provides stability to sand the object. Here is the image of the sander.
Due to the product demand and the CAGR, our estimated production volume is 80,000 per year. Our primary customers are direct users in industry applications, while our secondary customers are university workshops.
On this slide, you can see the bill of materials made up of 32 components, and on the right, the exploded view of the CAD.
Now coming to function analysis system technique diagram, the task function is to finish the workpiece either made of metal or wood. Here finishing workpiece involves different types of operations like shaping edges, smoothing surfaces, removing paint, removing excess material, etc. There are two primary functions. One is removing material and the other is to support the workpiece. The remove material function further branches out into basic functions, and then as you can see there are few supporting functions as well. Coming to the function component mapping matrix, you can see the columns defined by the functions on the terminal leaves of the fast diagram and the rows defined by name of all the parts of the products. The matrix helps to know which parts are involved in performing what functions. As it can be seen in the matrix, the highest number of parts are involved in performing the transmit power function.
Looking at the product family design, the sander will have different functions and components depending on the customer group. You can look at the different functions in the FDT on the left and different components on the right in the CCT.
There are two variations of the product based on the customer. Industrial manufacturers are the primary customer and the academic institutions are the secondary customers. As it can be seen in the figure and on the previous slide, there are few parts that can be considered as platform and the other parts that change depending on the application can be considered as module parts. The disk mount will be a common interface which will hold different type of disks depending on the application, and thus it forms the part of the platform.
The product family diagram shows the original version of the product. The original assembly sequence runs parallel.
For our product family assembly diagram, we are able to move the belt frame and motor to later in the assembly process, which allowed for more platform parts.
For our design for manual assembly, we started by analyzing each individual component and calculating the manual assembly time. For our redesign, we selected the base and motor support because they have some of the higher assembly times and give us a chance to consolidate. We also selected the frame because out of the modular parts, it has the highest assembly time. Furthermore, the quad chart shows that these parts are ideal for our redesign. As you can see, the base and motor support share the same functions of maintaining stability and reducing vibration, being ideal for part consolidation. Starting with the base and motor support, here you can see the CAD for the unedited parts, and initially the original combined assembly time was 32.26 seconds. We improved the base and motor support by reducing part count when we consolidated these two parts. We increased part symmetry and avoided adjustments in future assembly. These changes have no major effect in part function. The material cost did increase, but the number of parts decreased, which leads to lower assembly cost. Finally, we reduced the assembly time from 32.26 seconds to 14.72 seconds.
Here you can see the initial design for the belt frame prior to manual assembly improvement. The original combined assembly time is 19.95 seconds with a manual efficiency of 15%. Here you can see the modified part for easier assembly. We were able to reduce the number of fasteners in various positions. We also added chamfers to screw holes for easier alignment with the motor and added locating features so that we can locate the tensioner subassembly easier. This was able to decrease the assembly time from 19.95 seconds to 7.84 seconds. We were also able to increase the manual assembly efficiency to 38.3%. For automated assembly, we selected the subassembly of the table mounting, the belt table, the back plate, and the plate mounting. The function component mapping matrix shows that these parts all share functives that would provide the opportunity for part consolidation. This is the initial design before we made improvements to the automated assembly. The initial cost is $7.62. We consolidated the subassembly into one single part that can be formed with sheet metal. This reduced the part count, which decreased the assembly time. It also reduced the need for fasteners and does not need adjustments during assembly. Although the part itself is less adjustable in respect to the full assembly, it decreased the price greatly from $7.62 to $2.65.
For the process selection of the platform, we first defined the critical dimensions, which we decided were all of the drilled holes, since these are used for alignment with other parts. We used a tolerance of 0.127 millimeters for all dimensions, as this is typical for mill machining of steel. We chose to use plain carbon steel for this piece due to its strength and defined it as a non-circular prismatic shape. With the other dimensions and the economic batch size, we found that machining was the best option to manufacture this part. For the frame module, we selected the critical dimensions to be the holes, as they are used for alignment of the motor, as well as the height of the piece, as it's used for the length of the belt. We chose the tolerances to be 0.25 millimeters, as this is standard for metal die casting. Using the aluminum alloy A360, a non-circular prismatic shape, and the following dimensions, we found that there were 5 processes that fit our requirements. However, we chose to go with die casting, as this is a process that we covered thoroughly in class.
Now coming to the DfM for frame, which is a module part made of aluminium. Die casting is the process by which this part would be made. The key dimensions of the part and its orientation while die casting can be seen in the slide. The pre-DfM cost of manufacturing one frame was calculated to be $7.29. DfM guidelines 1, 4, 5, and 6 for die casting, as mentioned in the slide, were used to redesign the frame, and cost reduction of 4.2% was achieved without any significant impact on the function and assembly cost. As it can be seen in the images, design improvements like staggered ribs, number of side pulls reduced from 3 to 1, and smooth corners at all the intersections were made following the DfM guidelines for die casting mentioned in the previous slide.
The second DfM part we analyzed was the base. The base is made of plain carbon steel with the process of machining and has a total cost per part of $46.99 before any DfM changes. We use DfM Pro to identify several features to change, including using standard dimensions and designing holes to tool shape. Additionally, we decided to pre-shape by die casting for our part before milling it, as can be seen on the top right, in order to reduce the cost farther. This brought our total cost to $40.96. Analytically, we were able to reduce the cost of the base by 12.85%. Hubs had us reduce the cost by 4.71%, but we theorized that this could be because Hubs is unable to consider die casting as an intermediate step. Overall, the product function had no change, and standard screw sizes will make the assembling easier.
For the design for product service system, we have 2 targets. To reduce environmental impacts, we plan to use recyclable metal and handle the recycling process. We also use better motors to reduce energy consumption. To improve customer experience, we offer maintenance services to increase the life of the product. In addition, equipment is used to monitor when to renew the sander disc or belt. To summarize, after the redesign, we can significantly reduce the manual assembly time of the base and frame. We also save costs by changing the manufacturing process and optimizing the shape. Besides, the integration of the belt table helps reduce the cost of automated assembly. For further improvement, additional DfM for other parts, including the disc table and tensioner, should be applied.